Hello everybody, welcome back to our class, BJTE 2023 Electrical and Electronic Technology. Today we will look at a new topic of voltage. In a piece of copper wire, the electrons are in random motion with no direction. To produce a current flow, the electrons must all move in the same direction. To produce motion in a given direction, energy must be imparted to the electrons in the copper wire. This energy comes from a source connected to the wire. The force that causes the electrons to move in a common direction is referred to as difference of potential, or voltage. This chapter examines how voltage is produced. A current is produced when an electron is forced from its orbit around an atom. Any form of energy that dislodges electrons from atoms can be used to produce current. It is important to note that energy is not created. Rather, there is simply a transfer of energy from one form to another. The source supplying the voltage is not simply a source of electrical energy. Instead, it is the means of converting some other form of energy into electrical energy. The six most common voltage sources are friction, magnetism, chemicals, light, heat, and pressure. Friction is the oldest known method of producing electricity. A glass rod can become charged when rubbed with a piece of fur or silk. This is similar to the charge you can generate by scuffing your feet across a carpet in a dry room. A Van de Graaff generator is a device that operates using the same principles as the glass rod and is capable of producing millions of volts. Figure: magnetism is the most common method of producing electrical energy today. If a wire is passed through a magnetic field, voltage is produced as long as there is motion between the magnetic field and the conductor. A device based on this principle is called a generator. A generator can produce either direct current or alternating current, depending on how it is wired. When electrons flow in only one direction, the current is called direct current, DC. When electrons flow in one direction and then in the opposite direction, the current is called alternating current, AC. A generator may be powered by steam from nuclear power or coal, water, wind, or gasoline or diesel engines. The schematic symbol for a DC generator and an AC generator is shown in figure. The second most common method of producing electrical energy today is by the use of a chemical cell. The cell consists of two dissimilar metals, copper and zinc, immersed in a salt, acid, or alkaline solution. The metals, copper and zinc, are the electrodes. The electrodes establish contact with the electrolyte, the salt, acid, or alkaline solution, and the circuit. The electrolyte pulls the free electrons from the copper electrode, leaving it with a positive charge. The zinc electrode attracts free electrons in the electrolyte and thus acquires a negative charge. Several of these cells can be connected together to form a battery. Figure shows the schematic symbol for a cell and battery. Many types of cells and batteries are in use today. Light energy can be converted directly to electrical energy by light striking a photosensitive, light-sensitive, substance in a photovoltaic cell. Solar cell. A solar cell consists of photosensitive materials mounted between metal contacts. When the surface of the photosensitive material is exposed to light, it dislodges electrons from their orbits around the surface atoms of the material. This occurs because light has energy. A single cell can produce a small voltage. Figure shows the schematic symbol for a solar cell. Many cells must be linked together to produce a usable voltage and current. Solar cells are used primarily in satellites and cameras. The high cost of construction has limited their general application. However, the price of solar cells is coming down. Heat can be converted directly to electricity with a device called a thermocouple. The schematic symbol for a thermocouple is shown in figure. A thermocouple consists of two dissimilar metal wires twisted together. One wire is copper and the other wire is zinc or iron. When heat is applied to the twisted connection, the copper wire readily gives up free electrons, which are transferred to the other wire. Thus, the copper wire develops a positive charge and the other wire develops a negative charge, and a small voltage occurs. The voltage is directly proportional to the amount of heat applied. One application of the thermocouple is as a thermometer, also called a pyrometer. These devices are often used in high-temperature kilns and foundries. When pressure is applied to certain crystalline materials such as quartz, tourmaline, Rochelle salts, or barium titanate, a small voltage is produced. This is referred to as the piezoelectric effect. Initially, Negative and positive charges are distributed randomly throughout a piece of crystalline material, and no overall charge can be measured. However, when pressure is applied, electrons leave one side of the material and accumulate on the other side. A charge is produced as long as the pressure remains. When the pressure is removed, the charge is again distributed, so no overall charge exists. The voltage produced is small and must be amplified to be useful. Uses of the piezoelectric effect include crystal microphones, phonograph pickups, crystal cartridges, and precision oscillators. Note that although a voltage can be produced by these means, the reverse is also true. That is, a voltage can be used to produce magnetism, chemicals, light, heat, and pressure. Magnetism is evident in motors, speakers, solenoids, and relays. Chemical activities can be produced through electrolysis and electroplating. Light is produced with light bulbs and other optoelectric devices. Heat is produced with heating elements in stoves, irons, and soldering irons. And voltage can be applied to bend or twist a crystal. Cells and batteries. As mentioned in the previous unit, a cell contains a positive and a negative electrode separated by an electrolytic solution. A battery is a combination of two or more cells. There are two basic types of cells. Cells that cannot be recharged are called primary cells. Cells that can be recharged are called secondary cells. An example of a primary cell is a Leclanche cell, also called a dry cell. As in the figure, this type of cell is not actually dry. It contains a moist paste as the electrolyte. A seal prevents the paste from leaking out when the cell is turned sideways or upside down. The electrolyte in a dry cell is a solution of ammonium chloride and manganese dioxide. The electrolyte dissolves the zinc electrode, the case of the cell, leaving an excess of electrons with the zinc. As the current is removed from the cell, the zinc, ammonium chloride, and manganese dioxide produce manganese dioxide, water, ammonia, and zinc chloride. The carbon rod, center electrode, gives up the extra electrons that accumulate on the zinc electrode. This type of cell produces as much as 1.75 to 1.8 volts when used. A typical Leclanche cell has an energy density of approximately 120 watt-hours per pound. As the cell is used, the chemical action decreases, and eventually the resulting current ceases. If the cell is not used, the electrolytic paste eventually dries out. The cell has a shelf life of about 2 years. The output voltage of this type of cell is determined entirely by the materials used for the electrolyte and the electrodes. The AAA cell, AA cell, C cell, and D cell, as in figure, are all constructed of the same materials and therefore produce the same voltage. It should be noted that although the Leclanche cell is frequently referred to as a carbon-zinc, or zinc-carbon, cell, the carbon does not take any part in the chemical reaction that produces electricity. The alkaline cell is named because of the highly caustic base, potassium hydroxide, KOH, used as the electrolyte. The design of an alkaline cell on the outside is very similar to that of a carbon-zinc cell. However, the inside of the alkaline cell is significantly different. As in figure, alkaline cells have an open circuit rating of approximately 1.52 volts, and an energy density of about 45 watt-hours per pound. The alkaline cell performs much better over temperature extremes than carbon-zinc cells. Alkaline cells perform best where moderate to high currents are drawn over extended periods of time. Lithium cells, as in figure, have overcome the inherent properties associated with lithium. Lithium is extremely reactive with water. Lithium cell formation uses lithium, manganese dioxide, MnO2, and a lithium perchlorate, LiClO4, in an organic solvent. Water cannot be used. The output of a lithium cell is approximately 3 volts. Lithium cells are very efficient, with energy densities of about 90 watt-hours per pound. The greatest benefit of lithium cells is their extremely long shelf life of 5 to 10 years. A secondary cell is a cell that can be recharged by applying a reverse voltage. An example is the lead-acid battery used in automobiles. As in figure, it is made of 6 2-volt secondary cells connected in series. Each cell has a positive electrode of lead peroxide, PbO2, and a negative electrode of spongy lead, Pb. The electrodes are separated by plastic or rubber and immersed in an electrolytic solution of sulfuric acid, H2SO4, and distilled water, H2O. As the cell is discharged, the sulfuric acid combines with the lead sulfate, and the electrolyte converts to water. Recharging the cell involves applying a source of DC voltage greater than that produced by the cell. As the current flows through the cell, it changes the electrode back to lead peroxide and spongy lead and converts the electrolyte back to sulfuric acid and water. This type of cell is also referred to as a wet cell. Another type of secondary cell is the nickel-cadmium (NiCad) cell, as in figure. This is a dry cell that can be recharged many times and can hold its charge for long periods of time. It consists of a positive and a negative electrode, a separator, an electrolyte, and a package. The electrodes are comprised of a deposit of powdered nickel on a nickel wire screen, which is coated with a nickel salt solution for the positive electrode and a cadmium salt solution for a negative electrode. The separator is made of an absorbent insulating material. The electrolyte is potassium hydroxide. A steel conforms the package and is sealed tightly. A typical voltage from this type of cell is 1.2 volts. The ability of a battery to deliver power continuously is expressed in ampere-hours. A battery rated at 100 ampere-hours can continuously supply any of the following: 100 amperes for 1 hour, 100 times 1 equals 100 ampere-hours, 10 amperes for 10 hours, 10 times 10 equals 100 ampere-hours, or 1 ampere for 100 hours, 1 times 100 equals 100 ampere-hours. Connecting cells and batteries. Cells and batteries can be connected together to increase voltage and/or current. They can be connected in series, in parallel, or in series parallel. In series, cells or batteries can be connected in either series aiding or series opposing configurations. In a series aiding configuration, the positive terminal of the first cell is connected to the negative terminal of the second cell. The positive terminal of the second cell is connected to the negative terminal of the third cell, and so on, as in figure. In a series aiding configuration, the same current flows through all the cells or batteries. This can be expressed as I total equals I1 equals I2 equals I3. The subscript numbers refer to the number of each individual cell or battery. The total voltage is the sum of the individual cell voltages and can be expressed as E total equals E1 plus E2 plus E3. In a series opposing configuration, the cells or batteries are connected with like terminals together, negative to negative or positive to positive. However, this configuration has little practical application. In a parallel configuration, all the positive terminals are connected together and all the negative terminals are connected together, as in figure. The total current available is the sum of the individual currents of each cell or battery. This can be expressed as I total equals I1 plus I2 plus I3. The total voltage is the same as the voltage of each individual cell or battery. This can be expressed as E total equals E1 equals E2 equals E3. If both a higher voltage and a higher current are desired, the cells or batteries can be connected in a series parallel configuration. Remember, connecting cells or batteries in series increases the voltage, and connecting cells or batteries in parallel increases the current. Figure shows 4 3-volt batteries connected in a series parallel configuration. This configuration produces a total voltage of 6 volts with a current twice that of an individual battery. It is necessary to connect the 2 3-volt batteries in series to get the 6 volts. To increase the current, a second pair of 3-volt batteries is connected in series, and the resulting series-connected batteries are connected in parallel. The overall result is a series parallel configuration. Voltage rises and voltage drops. In electric and electronic circuits, there are two types of voltage: voltage rise and voltage drop. Potential energy, or voltage, introduced into a circuit is called a voltage rise. As in figure, the voltage is connected to the circuit so that the current flows from the negative terminal of the voltage source and returns to the positive terminal of the voltage source. A 12-volt battery connected to a circuit gives a voltage rise of 12 volts to the circuit. As the electrons flow through the circuit, they encounter a load, some resistance to the flow of electrons. As electrons flow through the load, they give up their energy. The energy given up is called a voltage drop. As in figure, the energy is given up in most cases as heat. The energy that the electrons give up to a circuit is the energy given to them by the source. To repeat, energy introduced into a circuit is called a voltage rise. Energy used up in a circuit by the load is called a voltage drop. A voltage drop occurs when there is a current flow in the circuit. Current moves through a circuit from the negative polarity to the positive polarity. The voltage source establishes the voltage rise from the negative terminal to the positive terminal. The voltage drop in a circuit equals the voltage rise of the circuit, because energy cannot be created or destroyed, only changed to another form. If a 12-volt source is connected to a 12-volt lamp, the source supplies a 12-volt voltage rise, and the lamp produces a 12-volt voltage drop. All the energy is consumed in the circuit. If two different lamps are connected in series, such as a 9-volt lamp and a 3-volt lamp and connected to the 12-volt source, as in figure, the 9-volt lamp produces a voltage drop of 9 volts, and the 3-volt lamp produces a voltage drop of 3 volts. The sum of the voltage drops equals the voltage rise of 12 volts. Ground as a voltage reference level. Ground is a term used to identify zero potential. All other potentials are either positive or negative with respect to ground. There are two types of grounds, earth and electrical. In the home, all electrical circuits and appliances are earth-grounded. Consequently, no difference of potential exists between any two appliances or circuits. All circuits are tied to a common point in the circuit panel box, circuit breaker or fuse box, as in figure. This common point, the neutral bus, is then connected by a heavy copper wire to a copper rod driven into the earth or fastened to the metal pipe that supplies water to the home. This protects the user from electrical shock in case of a faulty connection. Electrical grounding is used in automobiles. Here the chassis of the automobile is used as a ground. This can be verified by seeing where the battery cables are attached to the automobile. Generally, the negative terminal is bolted directly to the frame of the automobile. This point or any other point on the frame of the automobile is considered to be ground. Ground serves as part of the complete circuit. In electronics, electrical ground serves a different purpose. Ground is defined as the zero reference point against which all voltages are measured. Therefore, the voltage at any point in a circuit may be measured with reference to ground. The voltage measured may be positive or negative with respect to ground. In larger pieces of electronic equipment, the chassis or metal frame serves as the ground point, reference point, as in the automobile. In smaller electronic devices, plastic is used for the chassis, and all components are connected to a printed circuit board. In this case, ground is a copper pad on the circuit board that acts as a common point to the circuit. Thank you for listening to the presentation. If you should have any question, please feel free to ask. Thank you once again.